Hi everyone. Today we're going to talk about chemical reactions. You've already made it through naming and drawing structures for ionic and covalent molecules, so this is going to be the next step, reacting stuff together. What is a chemical reaction anyway? It is a process by which atoms of one or more substances rearrange to form different atoms or substances. So that is a bunch of fancy terminology to basically say we throw two chemicals together, they react, and they do stuff. Okay? So a chemical reaction is closely related to something you may have heard me reference before, the law of conservation of mass. So what that says is that matter can neither be created nor destroyed. So what that means to you is if we're reacting two substances together, all the atoms that are present in those substances, they don't go away and they don't form completely new things. Those atoms are rearranged into other substances, okay? So how do we know a chemical reaction has occurred? There are a few things that can indicate a chemical reaction. You could have a color change, a temperature change, there could be a smell, an odor, you could have gas bubbles coming out of whatever reaction you performed, or you could have the appearance of a solid or a precipitate. So the last one, that term precipitate, you may not have heard before, but basically what I mean by that is, let's say we reacted two liquids together and then you see this like solid chalky substance forming in the bottom of that reaction, that would be a solid precipitate. Any one of these doesn't necessarily mean that a chemical reaction is taking place, but it does indicate that a chemical reaction took place. So just because there's a smell doesn't mean a chemical reaction is going on, but it can certainly indicate that one might be. But if you have a bunch of different things like this happening at the same time, you're probably dealing with a chemical reaction. Okay, so how do we represent chemical reactions? Well, we have reactants and we have products, and we have an arrow in between them. So down here on the left side, we're going to have our reactants, what we are starting with. On the right side, we're going to have our products, or what we're ending with. And in the middle of them is an arrow that's going to point towards the product. So quite literally, if I were to read this reaction example out loud, I would read it: reactant 1 and reactant 2 yield product 1 and product 2. Alternatively, I could also read it: reactant 1 and reactant 2 react to produce product 1 and product 2. So that's how you would read a chemical reaction, and that's how you're going to know what's reacting with what to produce what things. There are a few symbols that you should be aware of, and I'm just going to kind of run through them real quick. I'm also going to redraw that sample reaction so that you have some context. So anytime you see a plus sign, like you see here and here, that is going to separate reactants from one another and products from one another. Anytime you see this arrow here, like you see right here in the middle, that's going to separate the reactants and products from one another, and it's going to point towards the products. But sometimes instead of this arrow, you might see a symbol like this. That's very similar to the reaction arrow, except what this means is that a reaction is happening in equilibrium. And so basically, if you see this, reactant 1 and reactant 2 are forming product 1 and product 2, but also product 1 and product 2 are turning back into reactant 1 and reactant 2. So anytime you see that double-pronged arrow, it means that the reaction is going in both directions. Okay. The other stuff down here, S, L, G, and A, Q, those are symbols that represent what state a certain thing is in. So if reactant 1 had this down below it, that would mean that reactant 1 is a solid. If reactant 2 had that, it would mean that reactant 2 is a liquid. If product 1 had a G, it would mean that that was a gas. And if product 2 had a Q next to it, this one is a little bit harder. What that means is that product 2 is currently dissolved in water. So if, let's say I had NaCl and it had AQ next to it, that means that the sodium chloride, the salt, is not just salt crystals that you're throwing into the reaction, it's actually salt water. It's salt dissolved in water. So that's what that means. One other thing that I want to point out is that the L here, I will often write it as a cursive L. And the reason that I do that is because a non-cursive L a lot of times will look like a 1. And I don't want anybody to ever confuse the two. So I'll write it in cursive just so that you know the difference. The last symbol that I would like you to be aware of that you probably won't see again for another couple of units is this triangle, also known as delta, and that stands for the heat in a reaction. There are a couple of different ways that I could represent chemical reactions to you. I could either represent a chemical reaction with a word equation, or I could represent it as a skeleton equation. So both of these examples are the exact same reaction. It's just that I have written the first one using words and I've written the second one using the chemical symbols. So I would expect you to be able to interpret the word equation. That's why we went through how to name ionic things, how to name covalent things, how to write the symbols and write the Lewis structures and everything for all of those things so that you could effectively interpret a word equation and so that you would know what these things are. So that's actually step 1 of the next thing I'm going to talk about, which is balancing. But if I tell you aluminum and bromine reacts to produce aluminum bromide, I would expect you to be able to write out this equation effectively. I would expect you to know to look at your periodic table to figure out that the chemical symbol for aluminum is Al. I would expect you to know that bromine is a diatomic element and therefore shows up as Br2. I would expect you to take aluminum bromide, realize that that is an ionic molecule because it has a metal and a nonmetal, and therefore you need to use swap and drop to make that compound. So you would need to do the Al plus 3, you would need the Br minus 1, you would need to swap and drop and turn that into Al Br3, okay? So I know that probably sounds like a lot, but we have practiced all of these skills. And if you are somebody who is confused, you don't remember how to do it, you need to come to me and we need to talk about it and get you some practice, because I will absolutely expect you to be able to do this from here on out until the end of the class. And if you don't know, that's going to be a problem. So try to write both the word and the skeleton equations from the samples below. You're going to give it a shot, and then we will talk about it. Okay, but I'd like to go over the steps of writing chemical equations and balancing them next. So step 1 of writing equations is going to be actually writing the skeleton equation. So if I said, for example, I wanted you to write and balance the equation for hydrogen gas and chlorine gas yield hydrochloric acid, I would expect you to be able to write that down. I would expect you to know, okay, well, hydrogen diatomic, chlorine diatomic. I would expect you to be able to come up with a formula by me saying hydrochloric acid. Okay, so those are, again, skills that if you don't know how to do that, you have to talk to me. So that's step 1, write the actual skeleton equation. Step 2 is going to be counting the number of atoms of each element in the reactant. So let me go ahead and really quickly redraw this skeleton from the previous slide. We have our H2, we have our Cl2, and that's going to yield hydrochloric acid. So our job now is to count. How do we count how many? we look at subscripts and we look at if there aren't any subscripts. You see this H2, it means there is 2 hydrogens. You see the Cl2, it means there's 2 chlorines. Here we have H and Cl. So on the right side, which is actually step 3 in the products, we have 1 hydrogen and 1 chlorine. So just looking at this, you're seeing an imbalance. You're seeing there's 2 of each on the left, but there's not 2 of each on the right. So just to rehash, step 2 and step 3, you're counting how many are on each side. And if they don't match, you're going to have to balance it out. Okay? Step 4 is actually to change the numbers of coefficients in front to make the 2 sides match. So let me again, I'm going to redraw that skeleton equation so we compare the balanced to the unbalanced one. So this one up there is unbalanced here. This one down here is now balanced, okay? So once again, we have 2 of each thing on the left. We only have 1 of each thing on the right. You can change the coefficients that are in front of the molecules. So there's essentially this blank space in front of each molecule here, here, and here, where you could theoretically put a coefficient. If you don't know what a coefficient is, you've absolutely heard the term before. So like in 2x, the coefficient is 2. In 3x, the coefficient is 3. It's whatever number is in front of your variable, or in our case, in front of your molecule. So right now, we don't have any coefficients in those spaces. So we can place one if we need one, okay? 2 hydrogens on the left, 1 hydrogen on the right. 2 chlorines on the left, 1 chlorine on the right. So the easiest way to balance this equation out to make sure that there's the same amount of stuff on the left as on the right is to place a 2 there. So I'm going to go ahead and draw that out down in this space down here to visually represent it, because I think some of you are probably going to really struggle to visualize this unless you can see it. So before I balanced that, what I was looking at on the left was I had, here's my H2, and I had, here's my Cl2, and I'll draw in the valence electrons real quick. But on the right, before I balanced it, I was just looking at this. Okay? So now here it's really easy to visually see there's 2 of each on the left, there's only 1 of each on the right. So in adding a 2 here, what I'm saying is that there's not just 1 HCl molecule on the right, there's actually 2, okay? Does that sound like I'm just creating molecules out of nowhere? It looks like that on paper, but in actuality, no reaction actually happens with 1 molecule, and 1 molecule. We're not ever going to get down to that scale. There's always excess. There's always more than 1 molecule just involved. So what you're saying is this is the ratio of what's going on. Okay? So let's just check our work real quick. We have 1, 2 hydrogens over here. 1, 2 hydrogens over there. That matches. Perfect. 1, 2 chlorines over here. 1, 2 chlorines over there. Perfect. We are balanced. We are not violating the law of conservation of mass. Our equation is copacetic. Okay? So step 5 and 6 are really just kind of quick things that you have to check. Step 5 is making sure your coefficients are in the lowest possible ratio. So let's say I had this situation instead of what I had before. Now we have 2, 2, and 4. All of those are divisible by 2, so you could quite literally just reduce by dividing everything by 2. It's the same thing that I would have had you do in the swap, drop, reduce when you're making an ionic formula. We want things to be in the lowest ratio possible. And step 6 is really just checking your work, making sure you did it right, okay? So next, I would like for you to look at these. These are my samples. These are written out for you but they are not balanced. So what I would like you to do is I would like you to pause it here and I would like you to see if you can try to balance some of these. If you can't and you can't figure it out, that's okay. I'm going to go over them in a second, but I would really like for you to try, because practicing is the only way that you're ever going to get this. So just give it a shot. And then if you can't do it, then that's okay. You can watch me do it and we'll practice together in class. So hopefully you took my advice and hopefully you paused it and you at least tried. But if not, we're going to go through it right now. There's a couple of tricks that I would like to give you really quickly that you may want to write down just on your notes separately. But I'm going to tell you right now, balance oxygen and hydrogen last. And it seems ridiculous, but if you try to balance oxygen and hydrogen first, it always turns into a pain. Oxygen and hydrogen are going to be the biggest pains to deal with, so try to balance them last. If you do that, probably 8 times out of 10, they're already going to be balanced by the time you get to them and you won't have to worry about it. But if you start with them, it just becomes an issue. The other tip and trick that I have to tell you is if you cannot balance it, if it is not working out at all and you cannot figure out, try multiplying everything by 2. Honestly, you guys, I don't know how many times I have just been so frustrated trying to balance something and then I multiplied everything by 2 and it suddenly worked out. It just does sometimes. A lot of times when you see that, that'll be a combustion reaction, and I'll tell you a little bit more about those when we get to them. But those 2 tricks have made my life a lot easier when trying to balance equations. But the method that you're going to use to do this is to move from left to right. That's the way that I like to do it. So if I'm just looking at an equation that's already written for me, I just move from left to right and I skip over oxygen and hydrogen. So right now on the left side of this equation, and I'm going to put like a little squiggly line to delineate that. On the left, I have 1 sodium. On the right, I have 1 sodium. Great, awesome. I don't have to add anything yet. We're skipping these for now. On the left, I have 1 calcium. On the right, 1 calcium. Okay. Cool. Still don't have to do anything yet. On the left, I have 2 bromines. On the right, now I only have 1 bromine. Wow. Now I have to do something. Remember, I can't change subscripts, but I can put a 2 here to make sure that there's 2 bromines now. Now the bromines match. But what I've done is I've thrown off my sodium. So what I need to do is I need to go back and compensate for that. I need to put a 2 and make sure there's 2 sodiums on the left and 2 sodiums on the right. Okay, so now all I have to do is I have to make sure that my oxygens and my hydrogens are still copacetic. So I have a 2 here. That means there's 2 total oxygens on this side. I have this OH2, which means there's 2 total oxygens on that side. 2 hydrogens on this side, 2 hydrogens on that side. We're balanced. Perfect. Moving on. Number 2, moving from left to right. 1 iron on this side, 1 iron on that side. Perfect. 3 chlorines on this side, only 1 on this side. So I have to put a 3 here. Okay. 1 sodium on this side. I just put a 3 here, which means there's 3 sodiums on that side. Uh-oh. I need to have a 3 there now. Now I've run out of atoms other than oxygen and hydrogen. But they're my last ones, so let's see. My oxygens on the left side, I put a 3 here, which means there's 3 total oxygens. There's an OH3, meaning there's 3 total oxygens. We're good. 3 hydrogens, 3 hydrogens. We are balanced. Number 3, 1 sodium on the left, 1 sodium on the right. 2 chlorines on the left, only 1 on the right, which means I need a 2 here. I've thrown off my sodiums now. I need to put a 2 there. And we're balanced. This one, 1 sulfur on the left, 1 sulfur on the right. My oxygens, there's a total of 1, 2, 3, 4 on the left and 3 on the right. Now, you may be looking at yourself going, well, how am I going to fix that? It's not that big of a deal. If you put a 2 here, 2 times 3 equals 6 total oxygens. On the left, we have 4. But look what I've done to my sulfur. I need to put a 2 over here to compensate for the 2 that I put there. So that's using the trick multiplying things by 2. Okay, so now I have 2 times 2 is 4, plus 2 more is 6. 2 times 3 over here is 6. So now my oxygens and my sulfurs are copacetic and we're balanced. This one looks kind of scary and long, but we're going to move from left to right once again. 2 potassiums here, only 1 over here. We're going to put a 2 there. 1 chromium here, 1 chromium here. We're good. I'm going to skip oxygen for now. 1 lead over on the left, 1 lead over on the right. Nitrogen. Now be careful with this one. Do you see how there's parentheses and a 2 on the outside? That means that there's actually 2 nitrogens here. And on the right, there's a 2 in front of KNO3, so there's 2 nitrogens. So I don't actually have to do anything else, okay? I don't have to add another coefficient. So now I've run out of things other than oxygen. I have 4 oxygen plus 2 times 3 equals 6 oxygen. So altogether I have 10. On that side, I have 3 times 2 equals 6 plus 4 more. And so I have 10 on the right. Lo and behold, we are now balanced. So I did that pretty quickly because I have had an insane amount of practice balancing equations. I don't expect you to be able to do it that fast, especially not trying it for the first time, okay? So if the way that I just did this does not make any sense to you, there are other methods that I can show you. They take a little longer, but if you're somebody that really likes to visualize entire molecules, I am happy to show you that method. You just have to come to me in either office hours or ELT and I can walk you through it. This, to me, is the method that makes the most sense and goes the fastest. But again, if that doesn't make sense to you, please come to me. I am happy to talk you through anything and everything, okay? So I hope that that was helpful for you. We're going to be doing this week some practice with building reactants and products. We're going to move stuff around using Legos. Next week, we are going to look at the different types of chemical reactions and do some more practice with balancing. So I will see you in class when I see you, and have a good day.